by the Department of Mathematics, Mepkoshlank Engineering College, Sivahasi. On behalf of our college, I cordially welcome today's resource person, Dr. A. Chandrashekaran Sir, Central University of Tamil Nadu, Tiruvarur, for being a part of this online workshop. He completed his UG and PG degree in mathematics in Ayanada Janakiammal College, Sivahasi. He awarded his PhD degree in IIT Madras, Chennai. He has more than 15 years of research and teaching experience in mathematics. In addition to that, he is a resident faculty in Mathematics Training and Talent Search Program. He got NBHM JRF and NBHM MSc Fellowship, and also he achieved CSIR JRF Fellowship and CSIR SRF Fellowship and INSA Summer Research Fellowship. He carried out research projects with a grant of more than 27 lakhs funded by CERT. He published 10 research papers in reputed international journals. He organized workshops and delivered lectures in national and international conferences. It is an honorable moment for our Department of Mathematics, Mepkoshlank Engineering College, to have your prestigious talk in today's session. With this few introduction, I hereby welcome Dr. A. Chandrashekaran Sir to deliver his lecture. Welcome, sir.
So I thank Mepco College, the Department of Mathematics, and in particular the team of people working in Department of Mathematics, Dr. Guruswamy, everybody, for inviting me for this lecture. I'm happy to be part of this, and I hope that the participants are from like kind of various people, students from MSc level, no, right? Guruswamy,
all levels are there. All
yes.
levels they are at
MSc level and some scholars are there.
Okay, thank you,
Faculty.
So, the understanding is I'm giving 2 talks on functional analysis, and another 2 more talks will be given by Murugan. So Murugan needs for his lecture, which is going to be on 4th. He needs bounded linear operators. So at least he wants you to be familiar with bounded operators. So my interest today is to discuss bounded operators. Okay. So in functional analysis, before going into the topic, I want to spend a few minutes on what we are going to do, or what is our aim. So see, the aim of this workshop is problem solving skills. So the essential thing I want to say something about that. So if you want to solve some problem or something, the first thing which you want is understanding of the concepts, the necessities I'm going to write down, a good understanding of the concepts, the second one is, this is the very important point. The second one is there are some certain standard tricks. The standard tricks is you always go back to what you know, right? These are something which I have learnt during my MSc or during my PhD days and my experiences in MTTS and other places. Okay, go back to what you know. And third one is always look at the basic version of the problem. In some sense, break the problems into smaller things so that you can solve the smaller cases and rebuild upon. Okay. Break the problem into smaller pieces and try to solve. For example, if you want to study something for some thing you have to prove for set of all functions, then you think about the basic cases, identity function, constant function, then one by one you can improve on. Okay, so that is the idea of this. So these are something which I feel are very much essential in problem solving. But apart from this, you also have to have the knack of doing things specific to different subjects. For example, analysis, you need a different type of thinking. For algebra, you need a different type of thinking, etc. These are the things which are essential. Okay. And in general, at every place, asking the correct question is very important. And if you have a problem, and where you start is also very important. Okay, these are some general talk, general ideas which I want to stress before going further. So today, let us go to the topic. Today, what my interest is? My interest is I'll start with in functional analysis. What are the things we study in general? We study linear vector spaces which are equipped with norms. And when you have norm, it is a metric space. Whatever you know for metric space will be true for nonlinear spaces also. Okay. And when you have a norm, am I there? Okay, my sharing is there. Okay. So nonlinear spaces are really important in functional analysis. And what happens in with nonlinear spaces? Okay, what happens with nonlinear spaces? If you see applied mathematics like PD, OD, and all, they will try to look at the solutions in some nonlinear space, and they will see whether they will first try to prove the existence of their solution in some particular nonlinear space, and then they will try to approximate it. So there are certain things which are important for a nonlinear space. The first thing is we need a nonlinear space, and we need for approximation we need some kind of convergence. Okay. So what they do in approximation is they will start with some iteration. They keep on doing some iteration, and this iteration has to converge. When you want the iteration to converge, you expect completeness. So essentially, you need complete nonlinear spaces. That's what we call Banach space. Some doubt? Somebody? Right. Okay. So we move towards Banach spaces, and then we also need to understand the functions, or especially linear functions between nonlinear spaces. Okay. Right. So today I will just assume that you know some of the basic things, and if you don't know anything, you may ask now. Okay, ask in between. I'll just continue with I'm not going to write down the definition of a norm. Okay. Let us assume that I have a vector space X, and this vector space is over a field, let us say some F. Okay. And then I have a norm on this, and this is a norm linear space. Okay. We call this a norm linear space. Some let us see some common examples of nonlinear spaces. Okay, what are the common examples? Because this we will be using regularly. Okay, okay. Let's the usual R power n, the Cartesian product of R. Okay, n tuples, all n tuples, and we have several norms on this. And in fact, in functional analysis, the first time what we prove is in finite dimensional spaces, any norm is equivalent. What is the meaning of equivalent? When I say two norms are equivalent, their topologies are equivalent. Okay. Let us do the definition and other things later. Okay. So Rn. Okay. So I'm not going to mention any norm here. Every norm is equivalent to the norm. Let us define a norm and say that to this norm everything is equivalent. For every x in Rn, then the two norm let us define. Okay. The two norm is summation mod xi square whole to this norm. Every other norm you define on Rn, it's going to be equal to this. It's true for any finite dimensional vector space, right? So if I have a finite dimensional vector space X, X is finite dimensional. space. Then for x belonging to x, there exists alpha I belonging to f as a vector space over this field f, such that x is equal to summation over I alpha I, let's say ui. Okay. Here u1, u2, etc. un, let's say n is the dimension, is a basis of x. So now this alpha 1, alpha 2, etc. alpha n, if I put it as a tuple, then I can, for every vector x here, I can associate a n tuple. I can associate an n tuple. Let me write down in the horizontal thing. Usually the vector means we always write it in a column vector. Alpha 1, alpha 2. And this is a unique representation. So this way, this vector space X is isomorphic to Rn or I'll say Fn. Okay, in our case, Fn. So fine dimensional vector spaces. All fine dimensional can go into this. Okay. The next common thing which we use or which we see in functional analysis is there are two types of spaces. One is function spaces, another is sequence spaces. In function spaces, I'm going to consider only two things, two function spaces for this talk, for today's talk. One is set of all continuous functions. Number two, let's say x equals c of a comma b, set of all real or complex valued continuous functions on a comma b. All right? Okay. This is one thing. Now, there are, see, one more thing to understand here. In functional analysis, we can actually define multiple norms on a particular inner product space. See, for example, in this X, I can define two norms. Okay, let us call this as norm. Let's say F belongs to X. Norm F1 is equal to integral 0 to 1 mod f of x dx. I think there is a problem with my screen sharing, right? Is it okay? It keeps on.
No, sir, it's not okay. It cut out between.
There is a problem, right?
Yeah.
Just a minute. Sorry for that. So please let me know if there is a problem. Okay, I'll try to. Just a second. Just a second. Just hold on. Sorry for the trouble. Can you see this now? Somebody please confirm.
Yes, sir.
Thank you. And is this a norm? Somebody can somebody say this? Is this a norm?
Yeah, it is norm and it should be A to B.
It will be
A to B, integration over A to B because
yeah.
function is.
Then I will restrict it to 0, 1 because the drawing pictures it is nice, and for some of the examples it will be useful. Right. And for similarly, I can also define another norm here. Instead of this, I will call this supremum T belongs to 0, 1 modulus of this or. What is this?
Infinite norm.
What is this?
Infinite norm.
Yeah, infinite norm, I know that. So first thing is when you talk about some norm, here actually in both cases there are one thing I have to check. First thing when I define something, I want to know whether it's well-defined or
It
not.
is greater. It is greater than 0, and it is equal to 0 if that pole ft is equals to 0.
So the first one is well-defined because it's a continuous function and I can integrate it. Second one, it is a continuous function on a closed interval, closed and bounded interval. So it is a bounded function, and I can find the supremum. Okay, on a compact set, I can find the supremum. Or supremum exists. So these are the things, and then I can once again I will ask questions whether I can prove that these two to be normal. Okay, as I told you in the previous case, in this case these two norms are not equivalent. Right? Is it true? Are they equivalent or not?
No, they are not equivalent.
Who is it?
No, they are not equivalent, sir.
Yeah. Can you say why it is not equivalent?
Under F1 norm, this space is not complete, but under the infinite norm, this space is complete. And I think that's the reason.
Right. So if I have equivalent norms, then you think that the completeness is preserved.
Sorry, I couldn't hear you. Excuse me.
So if we have two equivalent norms, suppose that I have a norm on a vector space so that it is complete, and if I choose any other equivalent norm, still it will be complete.
Yeah. Yes, sir. Yes, sir. I think.
Are you sure about it?
Yes. Not sure about things, but I think I don't.
See, that's a small verification, right?
Yes, sir, it is true only.
Yeah. Yeah, but it needs verification, right? So what do you mean by equivalence? So two norms are equivalent if
one norm can be obtained from another.
More than obtained from. Can you say rigorously what is the meaning of equivalence?
Bounded by like constant
What?
times of norm.
Yeah, constant times. Yeah, there is a small thing you have to be careful. There are just not one constant. We need to have more than one constant. Am I right?
Yes, sir.
Yeah. It should be something like there exists. Let me go to this. Equivalent norms. So two norms on a vector space. Norm and norm star are two norms on X. We say are equivalent if there exist constants C1, C2 both positive such that for all x in capital X, C1 times norm X star is less than or equal to norm X, which is less than or equal to C2 times norm X star. So to check completeness, what you have to check? You have to check every Cauchy sequence converges. So convergence of sequence, will it follow? Okay, that is these equivalence, will it take it? Okay, that's the only thing. Suppose I have this convergence with respect to the norm without that star, then I can use this part of the inequality. Sorry, this part of the inequality, because I am going to estimate with respect to norm star, and then I can take this C1 this side out the other side because C1 is positive, and I can use the convergence with respect to this. Okay, and similarly, if I want the other way around, suppose I have convergence with respect to star, then I will use this inequality, this side inequality, that is right side inequality. Okay, so that's what I. So what is the other? Yeah, let me define what are the other things which I will be seeing this time in this lecture. Example 2 is set of all polynomials. Example 3, X is set of all polynomials. Okay, polynomials are expressions of the form a0 plus a1x plus a2x square plus etc. an x power n, an not equal to 0. Okay, you collect all these kind of expressions and that form a vector space, and I can define, I can see these polynomials as functions, okay, on 0, 1, right? So here actually this x set of all polynomial functions, I can call this as polynomial functions on 0, 1, and this will be a subspace of C of 0, 1. And C of 0, 1, once I know that this is a subspace of C of 0, 1, I can also always inherit the norm defined on C of 0, 1. Whatever I define as a norm on C of 0, 1, I can bring that as a norm for this subspace also. Okay. And then the fourth example, these are called LP spaces. Okay. What is this LP spaces? This is a collection of sequences. Let's call them as xn, such that summation over n mod xn the whole power p is finite. So that is p summable sequences. P summable sequences. So this P is a number between 1 less than or equal to P less than infinity. So for P equal to 1, it is just the sum of the absolute values. Okay. It is finite. Right. That's the meaning of this sequence. And when P equal to 2, that's called square summable sequences. Okay. Right. So the norm on this thing is, let us call this sequence xn as x. Okay. The norm of x. Once again, there is a problem. Let's see. So if the problem repeats, please let me know. So norm x is defined as summation over n mod xn power p the whole power 1 by. Okay. And there is another sequence space associated to this, that is L infinity, that is collection of all sequences xn, collection of all bounded sequences. Okay. So this this sequence spaces have various things. Okay, for what is the norm here? So for x belongs to L infinity, norm x is. What is the meaning of this collection? So it is nothing but supremum over n mod x. See here, bounded means everything is bounded, right? And then we have the others things. I'm going to write some things. Okay, some subspaces of L infinity, some subspace of L infinity. That is subspaces of their first one, set of all convergent sequences. Number 2, set of all sequences converging to 0. See, in all these cases, please assume there are real sequences. Okay, in all the cases, assume real sequences. Let me write down here. Real sequences, bounded real sequences. Right. This becomes set of all eventually 0 sequences. Eventually 0 means after a finite stage, everything in the sequence is 0. After a finite stage, everything is 0 in the sequence. Right. Now I have explained all these, so I am not going to talk about the completeness and all. If you want, all these spaces are complete. Okay, except for one C of A comma B, which is not complete with respect to a particular thing. Polynomial set of all polynomials is not complete. Okay. So, but then in functional analysis, the advantage is we can always have a completion of a particular incomplete nonlinear space. For example, the so-called capital L of 0, 1. Okay. That is set of all Lebesgue integrable functions on 0, 1 or okay, L1, L of 0, 1, right? That is nothing but a completion of C of 0, 1. Okay, right. But then we are not going to that. Now what we are going to look at? We are going to look at operators or linear maps between two nonlinear spaces, and then we are going to ask, we are going to discuss about bounded linear operators with specific property. See, generally, whenever we study functions between two abstract objects, generally, whenever we discuss once again creating trouble. I'm sorry, is it so troublesome? Can you read what I'm writing?
Yes,
Guru,
we can read. We can read.
yeah. So I can just ignore this and continue, no?
Yes.
You can continue, sir. Continue,
Okay,
sir.
okay. Thank you. Sorry for the trouble. Okay, right. So essentially, what we do when we discuss functions between two abstract objects is whether it preserves the corresponding operations. Okay. For example, if you talk about functions between two groups, the group operation is there something which preserves the group operation, that's called homomorphisms. Okay. When you talk about functions between two linear spaces or vector spaces, we talk about whether it preserves the vector addition and scalar multiplication, and that is called linear transformation. Those are called linear transformation. Now, what additionally we want from this linear transformation? See, generally in metric spaces, what we do between two metric spaces, we look at the important thing is we look at some functions which preserves limit points. They are called continuous function. They are called continuous function. Now these are already we have linear transformation between two vector spaces, but then they are all non-linear spaces. When I say non-linear spaces, they also have this thing called they are also a metric space. I am also looking at continuity. Let us see whether something preserves continuity or not. Okay. Then we'll see what is happening. Okay. So what we are looking at is between two non-linear spaces, I want to look at some linear maps that preserves continuity. Okay. So to understand the continuous linear maps, we'll do some small work here. Let us start with some arbitrary linear maps, two vector spaces, non-linear spaces x and y, and then we'll talk about continuity of this. Okay. Okay. So once I have a norm or a metric on two sets, then I know what is called continuity, what is called uniform continuity, everything I know, right? So I don't have to recollect them for you. So let us try this. X and y are two non-linear spaces. T from x to y is a linear map or linear transformation. Then the following so what is happening here I will explain. Okay. The first one is T is uniformly continuous. B, T is continuous. C, T is continuous at 0. 0 is the additive identity of x. Okay. And then D, there exist some k positive such that norm of Tx is less than or equal to k whenever x belongs to capital X and norm X is less than or equal to 1. Okay. Number 5, there exists K positive such that norm of Tx is less than or equal to K times norm X for all X belonging to them. Just a second. Okay. Now, if I prove this, I will observe something interesting. Let us assume that this has been proved. Okay. Let us assume that this has been proved. Then what happens is, I observe from the last two conditions something strange. Okay. What happens is, let us consider a small a bounded set. Okay. Let S subset of X be bounded. What is the meaning of S subset of X be bounded? What do you mean by S bounded in this? Then every point in this, every point of S belongs to a open ball, centered at 0. Right? That means this is what it is. There exists some positive number K such that for all X in S, norm X is less than or equal to K. Right? Now what happens is, when I say this norm X is less than or equal to K, this is going to be somewhere here. Every point X is going to be bounded by some distance, some neighborhood at this point. Let us say this distance is some K. Okay, so if I want, I can draw a bigger circle and everything is here. Now, I want to scale all this X, this set S, and bring it into some smaller neighborhood with radius 1. Okay. So I am drawing a picture for illustration in R2. Okay. This is a circle. Now, what kind of scaling will bring everything here? So if I have this K is, what is this K? K is a positive number. What is the number? Yeah, please, once again, come again. Yeah, somebody answered this. Who is it?
If I divide by K, it will come under. If I divide that K, it will make it on the circle.
So this norm will be less than or equal to 1. Am I right? Yes. Now what happens when I divide by this K? This is going to be somewhere here. This S is going to be somewhere here. All right. So the picture is not exact, but then this is what is happening. Okay. Otherwise, I will call this as S by K. Right. Now, what does this condition says? Whenever this norm of X is less than or equal to 1, the image norm of Tx is also less than or equal to K. Can you see this? So, what it implies is, according to T, by this condition D, what I know is norm of T times X by K will be less than or equal to, so I have used some same constant here K. So instead of this K, I will choose to be this constant, the bound, I will make it some small m. Accordingly, I will change here this m. And even here, then it has to be m. Now what happens? I don't have to say this everybody understands this. T is a linear map, and okay, m is positive, so I can say 1 by m times norm of Tx. But what do we know? This norm Tx is less than or equal to k, so this is less than or equal to k by m, and k by m is positive. So what it says is the image of every point, right? Something is wrong, right?
So your voice is breaking.
Can you hear me now?
Yes, sir.
Yes, sir.
Yeah, thank you. Sorry. So I should have evaluated this in a different way. Let me choose. Let me write down in the next page, fresh page. For x belonging to capital S, what is norm of Tx? I want to estimate this. This is equal to m times, okay, norm of T of x by m. I am using linearity here. But then what I know about this is this x by m, norm of x by m is less than or equal to 1, and hence I know this is less than or equal to m times k. So what it says is the image of every point in this S is also bounded by this mk. Okay. So in other in the codomain, my set T of S, that is the image, is bounded by this distance. What is this distance? M times k. Okay. So this means, so the observation is continuous linear maps, okay, linear maps takes bounded sets to bounded sets, or in some sense it preserves the boundedness of a set under this operation. If you take a set and if it is bounded, then its image is also bounded, and that's why we call continuous linear maps are also called as bounded linear maps. Right. This is the motivation for bounded linear operators. This is the motivation for bounded linear operators. Now, the reason, the way I have written A, B, C, D, etc. in this theorem, that is T is uniformly, all these 5 statements are equivalent. It starts with T is uniformly continuous, T is continuous on X, T is continuous at 0, there exists K positive such that norm Tx is less than or equal to K whenever X belongs to X and norm X is less than or equal to 1. Another condition is there exists K positive such that norm Tx is less than or equal to K times norm X for all X belongs to X. In many places, the last statement E, many books, the last statement E is the definition of bounded linear operator between two nonlinear spaces. Okay, and this statement D is more or less, it is always useful to check whether something is bounded or when something is continuous or not. Okay, right. And if you see this, the order in which I have written it, the A, B, C, it is well known for any general function on a metric space. Uniform continuity implies continuity, and continuity on the whole space implies continuity at a particular point. So in particular, continuity at 0. So A implies B implies C is always known. It is enough to prove that C implies D and D implies C and E implies A. This is what I have to prove, right? So the whole idea of this is going to happen by an interesting property of vector spaces. What is the interesting property? I'm going to draw the picture and then the proof is going to be very immediate. Okay. This is what happens in linear maps. Okay. If I have a ball centered at X and radius R, okay, this can be always written as, right, X plus R times B of 0, comma 1. This is what the scaling, whatever we did know the last time we divided by M, okay, in our example to scale down, and scaling and translation, okay. Scaling is moving along the same line passing through origin, and translation is in any direction you can translate, okay. So suppose I have a ball centered at X and radius R. Now I have 0 here, I have 1 here, so I have a ball here. Now what I do is, first I will scale this in the sense I will make it smaller or bigger by multiplying by R. Okay, if R is bigger than 1, then I will multiply and this will become bigger. And then I will translate. The translate means I add X to every vector here. Every vector in the bigger ball, I will add X. Okay. So if you want, I can say this is the bigger ball. To each element in the bigger ball, X is added, and hence everything moves to this new ball. So this is what the whole idea of this proof is going to be, something like this. It's going to help here. Okay, right. So once again, I am going to show what is the meaning of this. I have to prove. I am assuming continuity at 0, and then I have to prove that this is what is going to happen. Okay, and I think I will leave this as an exercise for you. C implies D, D implies E, and D implies A. The reason why I want to leave this as an exercise is I have about 45 minutes maximum, and I have to show some examples, some important examples of bounded operators and unbounded operators, because for tomorrow's class you might require this. Okay, right. Let's go back and check some examples, quick examples. As usual, examples of, so you know why I call this bounded linear operators, right? So first example. The first example would be the simplest example. You consider let us consider the simplest example to be something like this. X is a nonlinear space. X comma some norm is here. Okay, right. Now I am going to define the simplest example is identity map from X to X. Okay. Is it bounded? Of course, it is bounded. The reason is why. Now I have to. Should I go back and check? It's better. I will show you. Condition. I can check two conditions here now. This D and DE. Both conditions can be checked. Okay. Whenever norm X is less than or equal to 1, the identity of X is once again norm X. In this place of K, I can choose K to be 1. And even here it will be the same thing. Okay. Right. It's easy to check. Okay. Right. So norm of I of X is equal to norm of X. That's enough. This alone is enough to verify. Okay. So let's not waste time. Let us go further. Okay. I'm going to define some non-trivial map. Okay. Let us consider a linear map T from C of 0, 1, the set of all continuous maps. Okay. On 0, 1 to R. Consider given F in how I am defining it, right? Given F in C of 0, 1, the image of F under this linear map T is nothing but F at 0. Because I need a real number, right? I need real number for this. Okay, F at 0. This map is continuous. To understand this, why this map is continuous, first thing you have to fix the norm on this continuous C of 0, 1. In C of 0, 1, the norm is infinity norm. What is the infinity norm? It is norm F is equal to supremum over T Now to understand this, consider this. The norm on R is modulus function. Okay, that's the norm on R. So modulus of TF is what I have to estimate. It is equal to modulus of F at 0, right? But what do I know for F at 0? This F at 0 or any other point, F evaluated at a particular point is going to be less than or equal to supremum over T modulus of 20. Right? See, supremum of a set of numbers will be always bigger than or equal to any element of that set where you are taking it. Okay? But what is this supremum? This is nothing but norm. Right. So now what I have is modulus of TF is less than or equal to, therefore T is continuous. So T is, this seems to be a very simple thing, right? Just hold on, my battery has gone down. So connect the charger. Shall we look at another example on C of 01 itself? Right. See, another example is this. Number 3, once again C of 01 with the norm I'm going to define something different here. Okay, something different here. The reason why I'm going to define this operator is the following reason. See, generally, when I have this let me define what the norm is. Okay, first I'll define what the norm is. What the map is. Then we'll discuss what is going to happen. Right. So infinity norm. With the one norm. So F belong to C of 01. Norm F1 is equal to integral 0 to 1 mod F of t. This is my norm. Now to define the linear map T, I need a continuous function K from 01 cross 01. Okay, right. So this function is given by some like K of t comma tau. Now given this K is continuous. Once again, please understand this K is continuous on where? On this closed and bounded interval in R2. That is 01 cross 01. It's a compact set. Once again, it is going to be bounded. So the maximum of this can be obtained. Let us assume that this number modulus of this, okay, it is bounded always by some number, let's say k0. Okay, as I told you, it is here on a compact set. It's going to have a supremum, and let us call that supremum as k0, and hence this will be right. Now to define t from C of 0, 1 to C of 0, 1, okay, C of 0, 1 to C of 0, 1. Now what will I do is, I will try to give you the following let us say f belonging to C of 0, 1, then G is equal to T of f is defined as, how is it defined? I am going to define using integration. Okay, we call this as integral operator. Okay, G of T is equal to integral 0 to 1 k of t comma tau f of tau beta. This is what it is. Okay. Now this map is well defined. This map is well defined because, why is it well defined? Can anyone say why it is well defined? It is nothing but product of two continuous functions. Okay, and hence it is continuous, and a continuous function can be integrated. Okay. Right. So now, to understand what is the meaning of whether this map is bounded or not, what is that I have to verify? I have to verify whether the image TF, has the property something, it is less than or equal to some k naught or k times something like this. Okay, so this I have to verify. So if I have to verify this, how will I do that? Okay, that's the meaning. Okay, so but what is norm of TF? It is norm of G, right? But what is norm G? G is defined as maximum t belonging to 0, 1. Okay, t belonging to 0, 1, modulus of integral 0 to 1 k of t comma tau f of tau beta. This modulus. Now what I will do? I will do the usual thing. I will take the modulus inside and I will put less than or equal to this maximum t belonging to 0, 1 integral 0 to 1 modulus of k t comma tau, and this modulus can be a further split f of tau. Sorry. Beta. Okay, that much is fine. Now, but then what happens is this k of t comma tau is bounded by some number k naught. Bounded by some number k naught. So this is less than or equal to k naught times, right? See now, once this k naught is removed, this maximum has no meaning. Because the maximum is going to be taken over t, and t is only available in the function k, in the definition of k. So I will write down this is less than or equal to modulus of, instead of modulus, it's not modulus, 0 to 1, modulus of f of tau d tau. Okay, but what is this? By definition of the norm, that is nothing but norm f, right? Norm f. So that is equal to k naught times norm f. So this, from the previous result by item E, T is bounded. T is bounded. Okay. So I hope everyone is following me. Is it okay with this? Are you all okay? If you have any doubts at this point?
Yes, sir.
Yes, sir. Fine.
Oh, thank you. This is one simple example. Another example which I am going to do is something like, let's go to some sequence spaces. See, I am always doing something in infinite dimensional spaces. What I will be proving later is, I'll just complete this. I'll come back and prove that any linear operator on a finite dimensional space, defined on a finite dimensional space, is always bounded. Okay, it's always bounded. So I'm just keeping it as a reserve. Okay, some non-trivial examples which you have to know. That's the reason I'm doing this. Okay. Let us first finish that finite dimensional case. Okay, then we'll go further. This is our third example. Fourth example. Okay. X is finite dimensional non-linear space. Y is any non-linear space. Y need not be finite dimensional. Okay. Then T from X to Y is a linear map. Then T is bounded. So to do this, I am going to do a small trick. What is the small trick is, I am going to define a new norm on X. Okay, I am going to define a new norm on X. Let norm for all X in capital X, I am going to define the new norm, that is norm X1. So don't confuse this one with the previous one norm. It is some other idea also I can use. Okay, let me use something else. Let us use this one and definitely this is, that's not a problem. Okay. Is equal to norm X. See, X comes with this norm. Okay. Okay. Norm X plus norm Tx. So norm of Tx is, this is Y norm. Okay, this so you have to understand this. Here, this X, this is the norm given in X. This Tx is norm given by Y. Try to understand this. Tx is an element of Y, and hence this is a norm at Y. Okay, norm at Y. Now this is a norm. First thing you have to verify is this is a norm. So first thing, it is sum of two norms, so it is always non-negative. Then you say it is equal to 0. When it is equal to 0, sum of two non-negative numbers is equal to 0. Each one is 0, and hence X will be 0. Try to understand. I am verifying. If norm X1 is 0, then X is 0. Okay. Then if this is 0, then this sum is also 0, but it is sum of two non-negative numbers, it is 0. That means individual is also 0. So norm X is also 0, so X is 0. And the other way is also true. And if I have some lambda X, I will take lambda on both places, both summands here. So the third property will also be verified. And then for triangle inequality, it will also be verified without any trouble. Okay, right. Now what I am going to use? I am going to use the property that this norm and this norm on X both are equivalent. I am going to use that these two norms are equivalent. That's the only thing I am going to use. Okay. What are the two things? I'm going to use norm 1 is equivalent to norm in X. Okay. This happens because X is finite dimensional. Because X is finite dimensional. See, I have not proved that when in finite dimensional space, all the norms are equivalent. Okay. So to prove essentially all finite dimensional norms are equivalent, all norms are equal. It's not a very difficult proof. It will take some 10 minutes. If time permits, I'll do that. Okay. Right. And otherwise, it is a good exercise for any of you. If any of you have good understanding of what norm is, what equivalence is, then you can try to prove it. Okay. Right. Okay, right. Because X is finite dimensional. That's what we are doing here. Okay. So how will I use it? So since it is equivalent, what I know is there exists some k positive such that norm X 1 is less than or equal to k times norm X. This much I know. But what do I know about this? I have to actually estimate norm of Tx, right? But norm of Tx will be less than or equal to this sum, right? Because norm of Tx is less than or equal to norm X plus norm Tx. Right? I'm adding some non-negative quantity. Okay, I should have written it the other way around because of the definition I'm writing. Norm Tx plus some non-negative quantity, but which is equal to norm X 1. But this is less than or equal to some k times norm X. Therefore, what? T is bounded. Therefore, T is bounded. Now, this finite dimensional case, this gives an interesting thing, interesting observation. Now, let's make some observation out of it. If you consider T from some finite dimensional space, let's say Rn to Rn, then any map Tx will be of the form Ax. Right? Let's say Rm to Rn, Rm to Rn, where A is a n by m matrix. Right? Okay, all these maps given by any matrix, all the linear maps defined by a matrix multiplication is always bounded. Okay, all linear maps defined by matrix multiplication is bounded. Okay, now in particular, suppose you consider T from Rn to Rn, then A is a square matrix. Yes, somebody wants to ask some doubt? Someone? Who wants to ask a doubt?
room number?
What is it?
First floor or second?
I think they are discussing.
Third year.
Now what is, suppose I have two linear maps, S, T,
year?
and let us say
Last year na நீங்க நம்பர் மாத்திருக்கீங்களா? இந்த நம்பர் வந்து third year hostel number.
somebody is talking.
யமுனா ஹாஸ்டல் கிடையாது, இது வந்து தாமிரபரணி ஹாஸ்டல் போட்டுருக்காங்க. இது தாமிரபரணி ஹாஸ்டல் மேம். ஆமா, நீங்க சொல்லுங்க, நான் வேணா அவங்கள பேச சொல்றேன். அவங்க பொண்ணு பேசினாங்களா?
Saami, are you there? Let's continue. Now, if Rn to Rn is there, then A is a square matrix. So, if S is another thing from Rn to Rn, such that S of x is equal to some Bx. So, here T of x equals Ax. Then, if you consider T composition S at x, it will be T of S of x, that is equal to A, B, x. Okay. Just matrix multiply. And similarly, S composition T, essentially these are not equal. Okay. I can consider this because they are square matrices. It will be S composition T of x, and this gives me BA at x. So we can talk about the product of matrices. So we have two boundary linear operators, then the product is also boundary linear. Okay. This can be even for a general thing. This is also true for general thing. T from x to y and S from y to z are bounded. Then S composition T from x to z is also bounded. The reason is, look at S composition T, norm of S composition T at some x. Okay. Let's start with x belonging to capital X. Then what happens? This is equal to norm of S of T of x. But since S is bounded, there exists a constant Ks, okay, Ks, such that Ks times norm Tx, right? But then since T is bounded, there exist constants Kx and Kt times norm x. So now you see this norm of S composition T is less than or equal to this constant times norm x. So this S composition T is also bounded. Now this actually gives an interesting thing among the boundary linear operators. If you consider all boundary linear operators from x to y, B of x comma y set of all boundary linear operators, then see the first thing observation is addition of two boundary linear operators will be still boundary linear operators, right? Okay. So T1 plus T2 at Tx, this norm will be less than or equal to norm of T1x plus norm of T2x, and this will be less than or equal to some K1 times norm x plus K2 times norm x. So that is equal to K1 plus K2 times norm x. So we can prove that it's a vector space. Now this vector space, so B of x comma y is a vector space. Okay. In addition to this, B of x comma y has a product. Okay. Well-defined product. So this leads to say that B of x comma y has an algebra structure. Because of the product. What do you know about the because of the product? This reason. if I have composition of two boundary linear operators, that is also a boundary linear operator. So let us consider this. Now we will generally consider, we'll consider this, not this y, because it is meaningless. So p of x, right? P of x. So this b of x is going to have a, what do you call, a algebra structure with this product. Okay, algebra structure with this product. Okay. Now, but then is it a non-linear space? Is it a non-linear space? To understand what is the norm on this thing, let us wait for some time. Okay, I have some few more minutes. I think I can continue. Let's see what is going to happen. Let us first define the norm on this space. See, in b of x, okay, I am looking at b of x, that is the sum of all operators from on x to x. I am restricting myself to this case because most of the examples tomorrow you will be seeing will be from x to x. All linear maps from x to x is what we will be seeing. Okay, right. So let us understand this non-linear space b of x. This b of x is, I want to define a norm. Okay, so we know that for any t belonging to b of x, okay, let's define norm on b of x. For all t belonging to b of x, what I am going to do is, we know that there exists k positive such that norm of tx is less than or equal to k times norm x, right? Now there will be more than one k, there will be more than one k that satisfies this property, but I am going to find the smallest k if it exists such that this happens. So if I am going to look at that smallest k, okay, if I am going to look at such a smallest k, then what will happen is, this should happen of course for all x. Okay, right, this should happen for all x. So if I am going to look at such an x, such a k, then I am going to call that k as a norm. Okay, and we are going to verify whether it is a norm or not. Whether it is a norm or not. Now let us consider this. Suppose such a k exists. Then norm of tx, of course, for x equal to 0, we can ignore it. Okay, when x is non-zero, norm of tx divided by norm x will be less than or equal to k. Okay, but what is this? This is nothing but norm of t times x by norm x. Okay, so that means what? I can rewrite this. In a way, okay, by replacing x by norm x by 1, norm of ty is less than or equal to k for all y belong, for all y such that norm y is less than or equal to, or norm y, here norm y equals 1. Right? So I am going to just consider this. Okay, such a k is going to be like this. It's going to happen like this. Now what is that I am looking at? I am looking at the smallest k such that this happens. So the smallest k such that this happens is nothing but this k is going to be the least upper bound of least upper bound or supremum of over norm y equals 1 norm y equals 1, norm of ty. Right? So this looks at, we look at this, we observed how I'm going to define the norm. Okay, this is what I'm going to call it as norm. So I define norm of t as supremum norm y equals 1 norm of ty. Okay? This is my norm. So is this a norm? That's the question. Okay, is it non-negative? Yes, it is non-negative. Supremum of non-negative numbers, it is non-negative. Then if this is 0, what is the meaning of this? If this is 0, ty equal to 0 for every y. So t is 0. When t is 0, the norm is 0. And once again, when I'm going to multiply by lambda, I'm going to multiply lambda this side. Inside the supremum, I can take this outside. That's going to work. And what about triangle inequality? If I start with norm of t1 plus t2, this will be supremum of norm of t1 plus t2 times y. Use linearity to write norm of t1y plus t2y. And we can, that needs a small tricky work. Supremum of norm of t1y, t1 plus t2 times y, we have to say it is less than or equal to this. So there also once again you will use triangle inequality. Okay. But then splitting that supremum into two sets is what you have to be careful. That is, what you have to prove is, will be in the for triangle inequality, you have to be careful with the proof of the following. Supremum over t over norm y equals 1 norm of t1 plus t2 of y is equal to supremum over norm y equals 1 norm of t1y plus t2y. Okay, this one is less than or equal to supremum over norm y equals 1 equals 1 norm of t1 of y plus norm of t2 of y. See, this is just application of triangle inequality because supremum of, I'm going to take a set and every number of that set is going to be bigger than or equal to that other, this number. So the supremum is going to be bigger. That's okay. But then what I need is, norm of t1 plus t2. I want this number, norm of t1 plus t2 to be less than or equal to norm t1 plus norm t2, right? If this has to happen, then I have to write it like this. Okay, this we don't know whether it is going to happen. Let me erase this and I will write. I have to write this is less than or equal to supremum over norm y equals 1 norm of t1y, this plus supremum norm y equals 1 norm of t2y.
Sir, your screen is not showing.
Screen is not visible, sir.
Okay, sorry.
Unable to see the screen, sir.
Just hold on a second. I'll just reshare it. Just a second.
Sir, if you have any problem while sharing your screen,
Yeah, I'm just trying. There is some suddenly something stopped working.
okay, sir.
Yeah, just a minute. Fortunate. Usually it will not happen like this.
Okay, sir, no problem, sir. But
Yeah. Okay, fine. I will explain what I wanted to explain, and how long this lecture can go. I think it's already 8, right?
yes, sir, 8, sir, 8 is if you want
Yeah.
to extend, it can take 5 more, 10 more minutes, sir. Otherwise, another.
And let
If
me
any problem,
explain
we'll stop now.
what I'm
Okay.
trying to say. Okay.
So can you explain that last part tomorrow?
No, tomorrow I think tomorrow there is no class.
Oh,
No?
so next lecture, in the next lecture.
In the next
Because,
lecture I can do, but then I explain
because
this.
screen is not visible, no?
Yeah, I'll just explain this. I'll summarize what I have said today. Is it okay?
Yes, sir.
Yes, sir. Okay, sir.
Yeah. So the summary is we have seen some examples of nonlinear spaces, okay, and some norms, and we have proved that we have seen examples of boundary linear operators. We have not even seen a single unbounded linear operator. So I will give an exercise for you. You try this out, okay? The unbounded linear operators. Consider the set of all polynomial map, set of all polynomials, and the other side also take the set of all polynomials. Okay, you take the derivative of a polynomial. If you differentiate a polynomial, okay, if you differentiate a polynomial of degree n, it will become an n minus 1 degree polynomial, right? N minus 1 or lesser, okay? N minus 1 degree polynomial. Now, what I am trying to say here is, now consider this as a linear map. Verify this is a linear map or not. And then verify that this map is indeed an unbounded linear operator. This map is indeed an unbounded linear operator. Okay? With respect to what now? I'm going to say it is a supremum now.
So,
with respect to the supremum now. So how you are going to verify is, I'll do the hint also. The hint is you have to look at some bounded set in this polynomials with respect to supremum now. Let us say polynomials on 0, 1. Okay, on 0, 1. Now polynomial functions on 0, 1. Okay. Now what you have to do is you have to look at some bounded set whose image is unbounded. Whose image is unbounded. That's what you are going to look at. Okay. That is your exercise for today. And try to prove that this norm which I defined for set of all bounded linear operators on Bx, it is a norm. The triangle inequality is a tricky part. Up to whatever step I have written is simple. Less than or equal to supremum of this. When I want to split the two supremums, that's a problem. Okay, that you can think about it, and we'll continue in the next lecture. Thank you. Sorry for the technical difficulties. I think I will try to resolve it in the next lecture.
Excuse me, sir.
Yes.
Okay, sir.
Some doubts?
Yes, sir. Please repeat the question, sir. Homework question, sir.
The homework question is only this. Try to verify that the linear map which I defined is not bounded. It is a discontinuous operator.
Okay, sir. Thank you, sir.
Okay.
Thank
And
you, sir.
we will also post some. I will try to give you before that before this. I will try to give some examples, some exercises separately.
Okay, sir.
Okay, sir, can I ask a doubt, sir?
Yeah. Thank you.
Sir, can I ask a doubt?
Yeah, please go ahead. Who is it?
Sir, actually, in our bounded linear operator definition, norm of T of x less than or equal to k into norm x, but you are restricted norm x is less than or equal to 1. So, in the sense, if it is bounded, it should be bounded for all the space, on the whole space. But why you are restricted on norm x is less than or equal to 1, sir?
No, I have not defined the bounded linear operator as like that. What I did is, I am saying it's a different case. There are 5 equivalent conditions for continuity. Am I right?
Yes, sir. That
final
case only we have a doubt, sir.
Yeah, in our definition, bounded linear operator means it is continuous linear operator. Am I right?
Yeah, that's fine, sir.
So one of the equivalent conditions says there exists a positive constant k such that norm of Tx is less than or equal to k for all x such that norm x is less than or equal to 1 and x is belonging to the space x. Am I right?
Yes, sir. Yes.
This condition means that it takes the closed unit ball to a bounded set. Do you understand?
Okay. Yeah, that's fine, sir. Fine, sir. I understood.
When you map the closed unit ball to a bounded set, when a linear map does that, because of the picture I drew, do you remember that picture?
Yeah, because of the linearity, you can divide that when you drag into the sphere.
Yes. Whatever open ball or closed ball you give, you can map it to some other bounded ball, bounded set.
By the linearity, you can go to distance, some other distance, or you can drag it on that. And also, I have one more doubt, sir. It is actually boundedness is in your usual real line to real line, or in a normed space is something I think differs, sir. Because I feel that if f is from R to R, I take identity function, and the norm is usual modulus norm. How we can say that one it is finite dimensional? How it is say bounded, sir? Because it is the identity function, and norm is modulus. I can take usual modulus.
What is this? Can you explain once again? Can you ask once again?
Sir, can I take linear transformation from R to R? R.
Right.
It is identity function. It is the identity function.
Yes.
Norm is actually modulus.
Okay.
But it is finite dimensional case. How I can say that identity function is bounded linear operator?
Okay. I have to explain here one point I missed. See, when I say bounded linear operator, it doesn't mean bounded function.
Oh,
the function is bounded means mod x is less than or equal to some constant for every x.
Yes,
that is a different thing. Okay. But here, if I want to verify this is a bounded linear operator, okay, it is identity x. Modulus of identity x. Identity at x is equal to identity at x is x. That is equal to mod x. But what I want, modulus of identity of x is less than or equal to some constant times mod x.
Yeah. Okay. I understood.
Here I have got
I got it, sir. Because in the norm, it is not says that some bounded number is beyond that one. But here they are given k is some norm x.
Is different from bounded linear operator.
Yeah. Okay. Fine. Clear, sir. Clear. Now it is clear. Thank you, sir. Thank you so much.
Anybody? Any
sir, thank you, sir.
Yeah, thank you.
Thank you, sir. We'll see the next class, next lecture, sir. Thank you for your lecture.
I will stop here.
Thank you, sir. Yes, sir.
Thank you, sir.
Thank you.
Thank you, sir. Thank you, sir.
Thank you. So I think I can leave the meeting, right?
Yes, sir. Now you may leave. We'll see next lecture, sir.
Please share the notes, sir. Actually, it will be very.
Definitely will share it there, sir.